So we're going to find the derivative of the cube root of 5x squared minus x plus 4. Cube root means a power of what?
1/3.
1/3. So this is 5x squared minus x plus 4 to the 1/3 power. And we could write this as y equals what? With u equal to what?
Y equals cube root of u.
Cube root of u, or u to the 1/3. I'm going to write u to the 1/3 just because we're going to use the power rule. But yeah, cube root of u, or u to the 1/3, with u equal to that 5x squared minus x plus 4 that's inside of it. So what's dy du? What's the derivative of u to the 1/3?
1/3 u to the negative 2/3.
Power rule, right? And what's the derivative of u? What's du dx? The derivative of u with respect to x should be 10x minus
10x
1.
minus 1.
Yep. And then this 1/3 u to the negative 2/3 means we're going to have a 3 in the denominator, and we're going to have our u value to the 2/3 in the denominator. So 5x squared minus x plus 4 to the 2/3, and we're going to multiply that by 10x minus 1. Good or no?
Good.
All right. Let's take a look at this one. We've got a couple of different things going on here, don't we? What do we have going on? We've got a product of two functions, 2z plus 5 to the 3rd times 3z minus 1 to the 4th. But then each of those we're going to probably need to use the chain rule to find their derivative. So what's the bigger outer rule that we're going to use here?
Product rule.
Product rule, and then within the product rule, we're going to probably have to use the chain rule. So if we want to find y prime should be, according to the product rule, it should be 2z plus 5 to the 3rd times the derivative with respect to, in this case, it's z, the derivative with respect to z of 3z minus 1 to the 4th, plus 3z minus 1 to the 4th times the derivative with respect to z of 2z plus 5 cubed. And I know my handwriting is close to atrocious. Just for your reference, this is a 2, this is a z. The z will always have a line for it, because otherwise my 2's and my z's would look very similar. So z's got a line through it, 2 does not, obviously. All right, so let's find these derivatives that we need. So 2z plus 5 to the 3rd is still 2z plus 5 to the 3rd, but how are we going to find the derivative of 3z minus 1 to the 4th?
Chain rule.
Chain rule. So this is, let's just call it y equals u to the 4th, with u equal to 3z minus 1. So what's that going to give us? 4u cubed, so 4 times 3z minus 1 cubed, times the derivative of u, which is 3. Everybody good with that?
Yep.
Okay. Then we got our 3z minus 1 to the 4th, and then to find the derivative of 2z plus 5 cubed, we call that y equals u cubed, with u equal to 2z plus 5. And so what should that be? It should be 3 times this u, which is 2z plus 5, squared, times what?
2.
Times 2.
Is it not cubed? Or is it
cubed or is it squared?
Squared. It was u cubed, right? So when we take the derivative of that, it's 3u squared.
Okay, thanks.
So 3u squared and then times it with u.
Oh, I get it. My bad. Yeah.
All right. So how are we going to simplify this down?
Factor out common common things, I guess. That
Yeah,
both-
common things, common crap. We got common crap in here. We got 2z plus 5 to the third here and a 2z plus 5 to the second. What's in common with those?
2z plus 5 squared.
2z plus 5 squared. We got a 3z minus 1 to the third and a 3z minus 1 to the fourth. What's in common with those?
3z minus 1 to the third.
3z minus 1 to the third. We've got a constant of 4 times 3, so that's a constant of 12 in there. And we got a constant of 3 times 2 in here. So we have a constant of 12 and a constant of 6. So what do we factor out of that?
6.
6. All right, so we've taken a 6 out of this constant of 12 on the left. So what's left is a 2. And we've taken a 2z plus 5 squared, which leaves us with what? Just the 2z plus 5. And we've taken out 3z minus 1 to the third, which takes out all of that 3z minus 1 to the third. So that's everything from the left-hand side. Everybody good with that?
Isn't it 3z minus 1 to the fourth on the left? Or is that a... Oh, sorry. I was looking at the wrong one.
Yeah.
Sorry.
I think you're one step
is
up
the
too
third.
high.
Yeah.
Yeah. And then on the right-hand side, if we've taken out 3z minus 1 to the third, that leaves us with 3z minus 1 to the first, or just 3z minus 1. We've taken out the full 6, and we've taken out the 2z plus 5 to the second. So all that's left is just a 3z minus 1. Everybody good with that?
Yep.
Okay, so now we got 2z plus, or 6 times 2z plus 5 squared times 3z minus 1 to the third. And here we got 2 times the 2z is 4z plus the 3z should be 7z and plus 10 and minus 1, so 7z plus 9. And that's a nice factored form of that there, yeah? Any questions or issues with that? Somebody said something in the chat that I must have missed a long time ago, and now my chat's not opening up.
It just says yes, you're okay.
Well, somebody sent something. Sometimes people send stuff privately, so I got one that's privately sent that asked, how did I get the times 2? So this times 2 at the end over here comes from when we take the derivative of 2z plus 5 to the third, that's y equals u cubed with u equal to 2z plus 5. So it's 3u squared, so 3u squared. And we have to multiply by the derivative of u, and the derivative of u is 2. So hopefully that helps. Sorry, I just saw that now, even though it was a couple minutes ago. Cool. All right. So any other questions on this whole thing? All right. Let's do this one. Once again, what do we have going on outside of this all? This is a product rule problem, 3x plus 1 to the 6th power times the square root of 2x minus 5. So that's product rule, right?
Yeah.
Okay. So we should have f prime of x is equal to 3x plus 1 to the 6th power times the derivative of root 2x minus 5. So how do we find the derivative of root 2x minus 5? This is y equals root u, with u equal to 2x minus 5. So the derivative should be 1 over 2 root u, so 1 over 2 times the square root of u, and then times the derivative of u, which is that 2. Everybody good with that part so far? And then the second half should be root 2x minus 5 times the derivative of 3x plus 1 to the 6th. And the derivative of 3x plus 1 to the 6th, I'll just write this over here. That's y equals u to the 6th, with u equal to 3x plus 1. So that derivative should be 6u to the 5th. So there's my 6. And u is 3x plus 1 to the 5th. And then times the derivative of u, so times another 3 out in front. Everybody good with that?
Yeah.
All right, these two should cancel, and so we end up with 3x plus 1 to the 6th over root 2x minus 5 plus, looks like 18 root 2x minus 5 and 3x plus 1 to the 5th. Good or no?
And we don't have to make any effort to simplify. Like this could be a final answer, this kind of long expression.
Yep, that is perfectly fine. If you're asked when does this equal 0 for like a horizontal tangent line, or when does it undefined for a vertical tangent line, you should be able to simplify it down. So I mean, we'd want to get a common denominator of root 2x minus 5. So I mean, we could do that. Let's do that. Get a common denominator, root 2x minus 5. So I got to multiply the bottom by that, and it means I got to multiply the top by that. So we'll just say squared on that. We'll clear out that square root. And then what do they have in common? They have a 3x plus 1 to the 5th in common. So we could write this as 3x plus 1 to the 5th times 3x plus 1 plus 18 times 2x minus 5 all over root 2x minus 5. And what would that give us in the end? Let's see if I can move this over a little. Apparently not. Oh, that's not going to work. It almost worked.
What happened to your 3x plus 1 to the 6th? I'm just curious.
So we factored out the 3x plus 1 to the 5th power, since they both
Oh, so when you do,
3x plus 1
okay,
to the 5th,
okay.
which just made it just a 3x
See
plus 1 on the inside. So now, sorry, I just trying to move that over so I didn't have to put this all on the new page. 3x plus 1 to the 5th times, this has got a 36x in it, plus a 3x, so that'd be 39x, and then what is that, minus 90 plus the 1, so minus 89, all over root 2x minus 5. And I mean, that's a better answer, but not necessary. Unless you're asked specifically to figure out when this equals 0, because then we can see that it's 89 over 39 and negative 1 over 3. Everybody good with that?
Wait, how did you get the 39x?
I think I had 18 times 2x, which is 36x, right? And then plus the 3x is
Yeah.
39.
Oh, okay, yeah. I missed that.
I thought that 2 was a 7. I got really confused for a
You
second.
see, I was like, well,
There we go. Is that better? Now that it looks horrible still, but more like a 2. There you go. Now it's a 2. All right, let's do this one. So what are we going to do with this one?
Chain rule.
We're going to use the chain rule. So what's the outermost function of this?
Tangent cubed.
Right, it's tangent cubed of this 4x. So let's, if we were to do this, tangent cubed u, with u equal to 4x, what's the issue? How do we take the derivative of tangent cubed u?
Product?
Say that again?
Would it be product rule?
Well, we could write it as tangent times tangent times tangent, and that's a product rule within a product rule, which is a little bit of a pain. We could use the chain rule with it, but then we're kind of having to work from the outside or from the inside out, and it's better to work from the outside in. So we want our y function to be as simple as we can make it. So is there a way to make my y function more simple than tangent cubed u?
Power rule. Could you use the power rule?
Okay, so what would I write then as my y function?
Cubed?
Just u cubed, right? And then what would u be?
Tangent
Tangent to 4x.
Tangent to 4x. Okay, so let's do it this way. This is going to work out better than the other because we want to get the simplest function for our y equals to begin with, and then when we take the derivative of this at the end, we might have to use the chain rule again, but it's better than having to like double up with the chain rule in the first step. So we want to do the chain rule a second time on its own rather than within the other part of the chain rule. Hopefully that makes sense. But what is dy du? It's 3u squared.
3u squared.
3u squared. So then we need du dx, but we can't do that because tangent 4x requires the chain rule. So du dx, if we were to rewrite this, then we could say that u is equal to what? The tangent of,
Tangent of u.
yeah, so we can't say u, let's use a different variable. Let's call it tangent of v, with v equal to 4x. So du dx should equal du dv times dv dx. Does that make sense? So we're doing the chain rule for just this second piece of it,
Yeah.
which will be secant squared v times the derivative of v, which is 4. So we need to multiply dy du times du dx. So we're going to multiply this by this. So if we do all the constants, that should give us 12. And then we should have u squared. And then we should have secant squared v. So we should have 12 times, let me parentheses there, tangent squared 4x, and then times secant squared of 4x. Everybody good with that?
Okay, what's the
Yeah.
12 tan 4x squared and the secant squared 4x?
So we had 12u squared secant squared v. You agree with that? Or no?
Yeah.
Okay, so from there, the 12, right, 12 came from the 3 times the 4. The u squared, well, we go and find what was u. U was tangent 4x.
Or are we just plugging in the values to u?
Yep, because we got to end up in terms of x, right? So if we had u squared, that's tangent squared 4x. And if we have secant squared v, that's secant squared of 4x.
Got it. Thank you.
Uh-huh. Any other questions on that one?
Yep.
All right, let's see if we can do this one. You guys want to try and do this one on your own? Find the slope of the line tangent to this curve at the point where x equals pi over 3.
Sure.
All right, go for it. You guys got that or no?
One more minute.
Okay. All right, so you wrote this first as y equals what?
U to the fifth.
U to the fifth with u equal to sine
Sine of
x. Good. So we should have got 5u to the fourth times cosine x, or 5 sine to the fourth x cosine x. Is that what you all got for your derivative?
Yeah.
Yep.
All right, cool. And so if we're going to evaluate that at x equals pi over 3, all we have to do is plug in pi over 3. So we got 5 times sine of pi over 3 to the fourth times the cosine of pi over 3. And what's the sine of pi over 3?
Square
Root 3.
over 2.
Root 3 over 2. So we got 5 times root 3 to the fourth power. What's root 3 to the fourth power?
9.
9, and then 2 to the fourth should be 16. And cosine of pi over 3 is a half. So what did you end up with? 45 over 32. Good or no?
Yeah.
Yeah.
All right, we getting the hang of the chain rule. See how we can apply it to things. Everybody doing all right with the chain rule? It's a very important rule. You have to understand it completely. Otherwise, the rest of this unit's going to be unpleasant. So let's find some horizontal tangent lines. This will give us some good practice on solving trig equations also, in case you're needing a refresher on that. We want horizontal tangent lines. What does that tell you? What does that mean?
Slope equals 0.
The slope of the tangent line is 0, and the slope of the tangent line is the derivative, right? So y prime needs to equal 0. So let's find y prime. How do we take the derivative of cosine 2x?
Chain rule.
Chain rule. So, right, our function, we'll just say y equals cosine u with u equal to 2x. And hopefully you're getting to the point where you can kind of do these real quickly with maybe without writing it out. But what is the derivative of cosine u?
Negative sine u.
Negative sine u.
Negative
So
sine
that's,
u.
right, so negative sine 2x, and then times the derivative of the 2x gives you negative 2 sine 2x. And then what's the derivative of plus 2 cosine x? That should just become minus 2 sine x. Everybody good with that? Okay. And we want to know when does y prime equal 0. So we're looking for when does that equal 0. And how do we solve this trig equation?
Maybe
Get rid
factor
of
out negative.
You guys kind of overlap. I think I heard somebody say get rid of the negative 2 first. Is that right? So if I divide everything, I could factor out a negative 2 if I wanted to, and then divide by negative 2. So that would just give me sine 2x plus sine x equals 0. Everybody good with that?
Yeah.
Okay, so then what?
Use a double angle identity.
All right, double angle identity. So 2 sine x cosine x, that's the double angle for sine 2x that you should know, plus sine x equals 0. Then what?
Factor out the sine.
Factor out the sine. Yeah, so sine x times 2 cosine x plus 1 equals 0. And a lot of times people want to divide by sine at this point. You can't divide by the trig functions because that eliminates some of the answer choices that you might have gotten. So we'll say sine x equals 0, and we'll say 2 cosine x plus 1 equals 0. And when does sine equal 0 on the interval from 0 to 2 pi? X equals 0, right?
0 and
x
pi.
and pi. And it would be 2 pi, but we got non-inclusive on the 2 pi up there, so we will ignore that. And what about this one? This one says that cosine x equals negative 1/2. So when does cosine equal negative 1/2? Which 2 quadrants will we get an angle for that?
Pi third.
Pi over 3.
Okay, it's not pi over 3, right?
In the
No, 2 pi over 3.
second and third quadrants.
Yeah, second and third quadrant. So one of those should be where the reference angle is pi over 3, which is 2 pi over 3. And then in the third quadrant, it should be
Pi over 3.
4 pi over 3, right? And if you remember, right, if the cosine is negative 1/2, that means that it's both this angle that I've drawn in blue, where this little piece here is pi over 3. So that makes it 2 pi over 3. And it's also this angle in green here, where this little angle right here is pi over 3. Right, so that'd be pi plus pi over 3, or 4 pi over 3. Everybody good with that? So far?
Yep.
Are we done?
Do we have to make an equation out of it now that we have? Or like,
Yep. Exactly. It says find the horizontal tangent lines. All we found was where they occur. Right, we know that there's one at 0, one at pi, one at 2 pi over 3, and one at 4 pi over 3, but we need to figure out what's the y value there, because that's how we find the horizontal line. So that's just a little bit more trig here. Let me give us a new page here. So for x equals 0, what do we get? Y equals the cosine of 0 plus 2 times the cosine of 0. So cosine 0 plus 2 cosine 0. Cosine of 0 is 1, and that's 2 times 1, so we get y equals 3 for x equals 0. Everybody good with that one?
Yeah.
For x equals pi, we end up with y equals the cosine of, it was 2x, right? So cosine of 2 pi plus 2 cosine pi. So what is that one? What's the cosine of 2 pi? That's also 1.
1.
And then cosine of pi is -1, so that's 1 minus 2. So we got y equals -1.
Yep.
And then what was the next one? We had 2 pi over 3, is that right?
Yeah.
So y equals the cosine of 4 pi over 3 plus 2 cosine pi over 3. So what's the cosine of 4 pi over 3?
-1/2.
-1/2 plus 2 times the cosine of, oops, that should have been 2 pi over 3. And the cosine of 2 pi over 3, like we just said a minute ago, is also
-1/2.
-1/2. So we got -1/2 minus 1. So we get y equals -3/2. Yeah.
Yeah.
Okay. And last one, we got x equals, what was it, 4 pi over 3.
Uh-huh.
And so we got y equals the cosine of 8 pi over 3 plus 2 cosine of 4 pi over 3. And if we're talking about the cosine of 8 pi over 3, what angle is 8 pi over 3 the same as?
2 pi over 3.
2 pi over 3. We can knock off the 2 pi from that. So what's the cosine of 2 pi over 3? It is
-1/2.
-1/2. And then this one is plus 2 times, and cosine of 4 pi over 3 is again -1/2. So this one comes out to be the same as the one we did in green there for 2 pi over 3. Yeah?
Yep.
Everybody good there? Any issues?
No.
All right. Let's do this. Actually, let's have you guys do this on your own. See if you can come up with some reasoning why the slope for every line tangent to this curve is always positive. So take a minute or two and see if you can figure that out.
Quick question. Can we do chain rule just on the denominator, or would we have to do it on the whole thing?
You've got to do it on the whole thing. So you could rewrite it as like 1 minus 2x to the -3 if you wanted to, and then use chain rule like that, or
Okay, thank you.
All right, we ready to talk about this one?
Yeah.
All right. So we probably wrote this as, I don't like that yellow. It's kind of a C. Y equals u to the negative 3. Is that what you guys did?
Yeah.
With u equal to 1 minus 2x. So our derivative should have been negative 3 over u to the 4, or negative 3u to the negative 4, times the derivative of 1 minus 2x, which is negative 2. So we end up with 6 over 1 minus 2x to the 4th power. And this is our derivative, right? So we'll say y prime. So y somebody needs to mute themselves there. Not sure who.
Sorry about that. Hold on.
That's all right. All right. So we got 6 over 1 minus 2x to the 4th. And so this represents the slope of the tangent lines. And so we should be able to see that if the numerator is 6, that's always positive. And the denominator should also be 1 minus 2x to the 4th power should also always be positive. So a positive over a positive is always positive. Everybody good with that or no?
Yep.
All right.
Could
Cool.
you have also used the reciprocal rule?
Yeah, you could have. So you could have called this, 1 over u cubed with u equal to 1 minus 2x, and then used the reciprocal rule for 1 over u cubed, and then multiplied by negative 2. You would have got the same thing. It would have required, I think, a little bit of simplification, but you would have ended up with the same. Everybody good with that?
Yep.
All right. Let's see. We got like 20 minutes or so, right?
Yeah.
All right. I know you're all, I'm sure, hoping that I'll just say we're done, but that's not going to happen. So let's take a look at this graph. Everybody sees this graph here, yeah?
Yep.
All right. So we got the limit. So we got e to the x minus 1 over x. And I want to ask you a question about this real quick. What does it appear that the limit as x approaches 0 of this function is?
Looks like 1.
It looks like 1, right? I'm going to tell you with 100% certainty that that limit is 1. I'm not going to prove it to you right now, but we're going to need that for something we're going to do in a little while. So the limit as x approaches 0 of e to the x minus 1 over x is equal to 1. That's not something you need to memorize. Just keep it in mind as we're going through stuff today. All right, everybody good with that? It is 1. It looks like 1. It is 1. I promise you it's 1. I could prove to you it's 1 in a way that I haven't taught you yet, but it's 1. Everybody good? We're going to say that that's 1.
Memorize this.
Don't need to have that. You don't need to memorize that. Just keep it in mind as we go through stuff today. By the end of this unit, you will be able to show that that's 1 in about 3 seconds algebraically. So not a big deal if you memorize it right now. Let's find the derivative of this, e to the x. So is this one that I've given you a rule for?
Power rule.
Power.
All right, power rule
Yep,
seems
power rule.
like what you would think. how have all of our power rule ones looked like? They've been like x to the 4th, right? Or x to the 315th power or something, right? Where our variable is the base and our number is the exponent, right? Our integer is the exponent. Well, here our number is the base and our power is the variable. So the power rule only works when you have real number exponents. And in this case, we do not have a real number exponent, we have a variable exponent. So unfortunately, we cannot use the power rule.
Can you do natural log?
Okay, so that's a good thought. And if we were to take the natural log of both sides, what would you get? You'd get natural log of y is equal to x. True?
Yeah.
Yeah.
Okay, so now if I wanted to take the derivative of this, the derivative of x is easy, that's just 1, right? But the derivative of the natural log of y with respect to x, right? If we're trying to take the derivative with respect to x of both sides of this, that's easy. But this side, first off, how are we going to take the derivative with respect to x of something that's in terms of y? And second, we also haven't learned how to take the derivative of something with a natural log, right? It's a little bit of an issue there. But it's a good thought. And I'm not sure who said that because I can't see your faces or your names or anything when I'm sharing the screen. But I want whoever said that, keep that in mind as we move into later stuff today or the beginning of what we do tomorrow.
Okay.
Or sometime in the near future. We'll see what day it ends up being, but that's not going to work for us now. So let's see if we can think of something else. I mean, we're looking for a derivative, right? And we don't seem to have a good way to find it. So if we don't have a good way to find the derivative, what do we normally do? Besides sit and cry and give up. Chain rule, the only issue with the chain rule is what we do. We call this y equals e to the u with u equal to x. Or maybe y equals u with u equal to e to the x. But then we still have to take the derivative of an e to the u or an e to the x. So that's still a problem. What else have we done to find limits?
Oh, limit.
Limits, we've done limits, right? So let's look at the limit as what approaches 0?
8.
X. Oh, H. Yeah.
Limit as h approaches 0 of f of x plus h. So that'd be e to the x plus h minus e to the x all over h. Yeah?
Yeah.
Let's plug in the 0. What do you get? You get 0 over 0, right? So that's a problem. So how are we going to simplify e to the x plus h minus e to the x all over h?
Could you break up e to the x plus h into e to the x times e to the h? I don't know if that would do anything, but
Yeah, I mean, it's worth a shot at least, right? I mean, there's not really anything else we can do with that at the moment in the form it's in. There's nothing to like, I mean, there's literally nothing else to do to it to change how it looks, I don't think. Everybody agree that this should be the same? Right, because if I have the same base and I'm multiplying them together, you add the exponents, right? So e to the x times e to the h is the same as e to the x plus h. Okay, so now, who was that said that?
I said that.
Oh, perfect. Okay, so
Alex.
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 Yes.
All right. Revelinsky. Yeah, is that who that is? Yeah.
Yeah.
Okay. All right. So what are we gonna do with that, Alex?
Factor out e to the x.
All right. Good. So now they have that e to the x in common. So we'll take out the e to the x times e to the h minus a 1 all over h. And what can we now do? This was your master plan from the beginning, right, Revelinsky?
Sure. Let me see. No idea. Need some help on this one.
Oh no, somebody help him out. What can I do with this?
Looks like the thing from the beginning.
Part of it looks like this thing from the beginning, except instead of x's, I have h's. So if I've turned this into two separate limits being multiplied together, like, hopefully like that, what do you know about this second limit?
It equals 1.
It equals 1. And what's the limit as h approaches 0 of e to the x?
E to the x.
E to the x.
It's just e to the x. So you have e to the x times 1, which is e to the x. So the derivative of e to the x is e to the x. Is that okay?
Might be.
Yeah, there's nothing wrong with that. We didn't do anything wrong. Derivative of e to the x is e to the x. It is one of only two basic functions where the derivative of it is itself. I mean, like, for example, if I had 2 e to the x, the derivative of 2 e to the x should still be 2 e to the x, right? Or the derivative of any constant times e to the x should equal e to the x.
Yeah.
That constant times e to the x. What's the other function when you take its derivative and you get itself? Anybody think of it? We've already done it.
0.
Yeah, 0. If you take the derivative of 0, you get 0, right? But important rule that you're going to want to know and memorize, the derivative of e to the x is equal to e to the x. Okay? You will memorize that. I'm going to give you a sheet of all the derivatives. Once we've learned all of the derivatives I want you to know, I'm going to give you a sheet with all of them to memorize. But this is one you want to know for sure, along with all the trig functions, right? E to the x's derivative is e to the x. Any issues or questions on that? All right. So the derivative with respect to x of e to the x is e to the x. If we were to try to take the derivative of e to the u, so e to some function, this is just the chain rule. We can apply the chain rule into this. The derivative of e to the u is just e to the u times the derivative of that exponent times du dx. So let's do a couple of these real quick. It should be pretty easy. This is y equals e to the u, right? So we can say y equals e to the u with u equal to x cubed plus 5x, which should give us a derivative of the derivative of e to the u, which is e to the u, times the derivative of u, which is 3x squared plus 5. So our answer should be e to the x cubed plus 5x, all times 3x squared plus 5. Everybody good with that or no?
Yeah.
So with any luck, we should be able to do this one without writing any work out, I hope. I'm gonna try not to write the chain rule as much as I had been in the past, but especially for ones like this where it's e to the u, well, we know that we should end up with just this same thing, right? To start with, the derivative should be e to the x squared plus sine x. And what do we need to multiply that by?
2x plus cosine x.
2x plus cosine x. We're going to multiply it by the derivative of that exponent, right? So e to the u, or e to the x squared plus sine x, times the derivative of u, times the derivative of x squared plus sine x. Everybody good with that or no?
Yep.
All right. Let's see if we can find the derivative of a to the x. Any thoughts on how we're going to go about doing that one?
Do we do limits again?
We could do limits, but we don't have a specific one that we know to be true. I think we should better do this in a different way. I think we should better do this in an easier way.
Chain rule,
Okay, how?
like we were doing before, except now we have an a for a variable.
Right, but that's the one we previously did was just a very specific case.
It doesn't
with
work for
e
all.
to the
It
x.
only works
doesn't
for e.
necessarily-
Okay.
Right, it only works for e. Exactly. So any other thoughts on what we might do with that?
Power rule doesn't work here, right? For the same reason as the last one.
Yep. All right, so
Okay.
earlier today, somebody told me to do something, and I said, think about that for later. What did you tell me to do?
To do logs?
Yeah, so let's do that. Let's take the natural log of y, and let's take the natural log of a to the x. So on the left-hand side, we end up with natural log y, but on the right-hand side, what can we do to rewrite that?
It becomes x natural log of a.
Good, okay. And now let's go back in and let's exponentiate these both. So let's rewrite this as e to the natural log of y is equal to e to the x natural log of a. Everybody good with doing that?
Yeah.
And then e to the natural log y is y, right? So we have y equals e to the x natural log of a. Everybody agree with that?
Yeah.
And what does that now look like? It looks like y equals e to the
X, like they're e to some equation.
right, e to some function, e to the u, right? We've got y equals e to the u with u equal to x ln a. And how do we differentiate e to the u? It's just e to the u times the derivative of u. And what's the derivative of x times natural log of a?
Natural log of a.
It's just the natural log of a. So times natural log of a. And what's e to the u? Well, e to the u was e to the x ln a times the natural log of a. What's e to the x times natural log of a? What is e to the x natural log of a equal to?
A to the x.
the same as a to the x, right? So we could say that this becomes a to the x times the natural log of a. So the derivative of any number to the power of x, 2 to the x, its derivative is 2 to the x times the natural log of 2. The derivative of 3 to the x is 3 to the x times the natural log of 3. The derivative of 1,000 to the x is 1,000 to the x times the natural log of 1,000. Everybody good with that? Or no?
I have a question about the derivative of x times the natural log of a.
Okay.
So like in the red text.
Yeah, over here, this.
Yeah.
What's natural
Why is that
log
just
of,
the natural log of a?
right, so what's a? A is a number, right?
Uh-huh.
And what's the natural log of a number? It's just some other number, right?
Yeah.
So I have some number times x, and the derivative of some number times x is just that number, right? Derivative of 5x is 5. Derivative
Oh.
of 1,000x is
Okay.
1,000. Derivative of natural log of a times x is just natural log of a.
Okay.
Yeah, I think you
got
got to
it.
remember that that's just a constant. It's just a number out in front of that derivative. So it
Okay.
doesn't, it just hangs around once we get rid of the x from our derivative. Good.
Got it.
Can you explain the first couple
Okay.
steps again?
Yeah, so first thing we did was said we're going to take natural log of both sides. So that gives us natural log of the left and natural log of the right. And then one of the rules for logarithms is that if you have natural log of something to a power, you can take that power and pull it out in front of the natural log as a coefficient.
Okay, yeah.
That's why the x comes out in front. And then at that point, we said, well, this is still not any good to us because we can't take the derivative with respect to x on the left side for sure. We could do it on the right-hand side, but we can't do it on the left-hand side. But if we rewrite this as e to this power and e to this power, then that turns this back into a y, and it gives us e to the u, which we know how to differentiate. Does that
Got
help?
it. Okay. Yeah.
Cool.
Can you explain how you got a to the x from e to the x natural log of a?
Well, after all that work that we'd done, right, we ended up with all this work that I wrote in black, we got y equals e to the x ln a, right?
Mm-hmm.
Were you good with that?
Yeah.
Okay, well, we also know that y is equal to a to the x, right?
Uh-huh.
So if y is equal to a to the x and y is equal to e to the x ln a, then e to the x ln a must be equal to a to the x since they're both equal to y.
Oh, I see.
Right, I mean, and that's just the, we did all this work here with taking the natural log, pulling the exponent out, raising it as a power of e. To get that, I mean, we could do all of those same things in reverse if we wanted to. We could rewrite y as e to the ln y and reverse all those steps and get back to y equals a to the x. But we already knew that y was equal to a to the x and y was equal to this, so we just can say they're the same.
Okay, thank you.
Yep. Any other questions on that? This is another derivative you're going to want to have memorized. All right, let's real quickly take a couple of these derivatives. What time are we supposed to end at 27? Is that right?
Yeah.
All right, we got 1 minute. We could do this. So if we want to find the derivative of 3 to the sine x, that's 3 to the u. So, oops, I don't know why I just wrote a u. We can just apply the chain rule, and this is the extension of that using the chain rule. So we've got y equals 3 to the u with u equal to sine x. And so the derivative of 3 to the sine x should be the derivative of 3 to the u, which is what? 3 to the u times what?
Natural log of 3.
Natural log of 3. And then times the derivative of u, which is cosine x. So the derivative of 3 to the sine x should be 3 to the sine x times natural log of 3 times cosine x. Everybody good with that?
Yeah.
All right. And we'll do this last one and then we'll get out of here. So y equals 7 to the x squared cosine 5x. So this is y equals 7 to the u. Oops, u equal to x squared cosine 5x. So far good or no?
Yeah.
And what's the derivative of 7 to the u? It's 7 to the u times the natural log of 7 times the derivative of x squared cosine 5x. And that one will have to use what rule?
Product.
Product rule. So x squared and then the derivative of cosine 5x. Well, the derivative of cosine 5x, that's cosine v, let's say, with v equal to 5x. And so that should become the derivative of cosine is negative sine of v, so negative sine of 5x. And we'll throw that 5 in from the derivative of v, negative 5x squared sine 5x. And then plus 2x, the derivative of x squared, cosine 5x. And that's the derivative. Long and a little bit of a pain, but not too terrible, hopefully. Everybody good there?
Where'd the -5 and the coefficient come from?
This negative 5 right here.
Yeah.
So the negative came from the derivative of the cosine of v, that's negative sine of v.
Oh.
And then the 5 came from the derivative of the v. Does that make sense?
Yeah.
Cool. Any other questions? Any other questions, you can stick around. I know we're like 2 minutes over, so you probably want to just get out of here and go to your next class. There's not going to be an assignment due today. I will later this afternoon, early evening, put up an assignment that will be due tomorrow. You'll be able to do part of it, but you won't be able to complete all of it yet because we need to cover derivatives of logarithmic functions and inverse trig functions, which we'll do tomorrow. We'll cover that before you can complete the whole assignment, but you'll be able to do the first half of it when I post it up. Probably late afternoon, but it depends. I got stuff going on with my kids, so it might not be till like in the evening sometime. If you have questions, hang around. Otherwise, go to your next class. Have a good day.